and welcome to video 2.2, and in this video we're going to be talking about the very basics of measuring and using something called significant figures. Okay, so let's start at the basics of measuring. So you probably know how to measure volume of a liquid when it's inside of like a graduated cylinder or a beaker. And you may have heard the term meniscus before. Meniscus refers to the slight curvature of water when it's inside of a glass tube, especially a small tube. So in smaller tubes, what happens is liquids, they have a lot of cohesion and or really adhesion, where the molecule particles are really attracted to the glass, and so they kind of start to climb up the sides of the glass. And so as you see, it's climbing up the sides of the glass. It kind of makes this like smiley face with the liquid. You always want to measure the very, very bottom of the meniscus. So if I'm looking here, and sometimes the meniscus looks like it's 3D, so sometimes it'll look like, let me see if I can draw it here. It looks kind of like that, so it looks like a really thick meniscus. Always measure the very bottom line right here. So this is the line I'm going to be measuring on my graduated cylinder. I don't look at the top of the meniscus. I don't look at the top of the curve. I don't look at the sides. I look at the very, 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 very bottom of the curve. Here's another picture of a meniscus. So here I'd be reading this line right here, the very bottom of the meniscus. So there's three basic ways we can measure liquids. We can measure small liquids, or we can measure larger liquids. So to measure small liquids, you're going to use one of these two pieces. A graduated cylinder, which has little increments on the side, okay, that help you to be very specific in your measuring. Usually, graduated cylinders measure less than 100 mils, okay? So usually they measure between like 50 and 100, but they're very, very specific, and most of them you can measure to the ones place. So I can measure like 99 milliliters, or I can measure 98 milliliters, okay? The pipette is also used to measure small liquids, but it's not used to measure small liquids to fill your container. It's used to measure small liquids that you're dropping from your container. So for example, the way you read a graduated cylinder is you read, the numbers here are messed up, sorry about that. It says 0 at the top and 20 at the bottom. Sometimes on graduated cylinders, you'll have two sets of numbers. So you'll have a set of numbers that go 0 all the way down to 20. Those set of numbers are not very helpful to you, okay? So you're going to want to look at the set of numbers that go from 0 on the bottom all the way to 20. And they're probably on the other side of this graduated cylinder. I kind of chose a bad picture, but you always want to read your numbers going from bottom up, right? All the time, bottom up. So how much do you have in your container? Read bottom up. A pipette is opposite. Pipette, we're going to read basically top to bottom. A pipette, we're interested to know how much liquid have we dropped. So down here, our number here is actually 10, way down here. At the very top of the figure, if we go all the way to the top, we would see the number 0, okay? 0, if I filled it all the way up to 0, it doesn't mean I have 0 in my pipette. It means I have 0 in this container underneath the pipette, okay? And you can drop little drops from the pipette. As I'm dropping it, my level is actually going to go down, right? My liquid's going to go down as I'm dropping it. So we read from top to bottom to see how much we've dropped. So I'm not going to say that I have 9 point whatever in this pipette. I'm going to read it going top to bottom. So I'm going to say I have 8 point something that I've dropped into my smaller beaker. So pipettes, you read top to bottom. Everything else, you read bottom to top. Including beakers. So beakers are what we measure large liquids in because they're not very precise. There's three types of volumes you can measure. You can measure volume of a liquid like we were talking about, but we can also measure volume of a regularly shaped solid. So it's got to be like a square or a rectangle or something with height, width, and length. If you have an object with height, width, and length, then you can find volume by just using this formula here that I'm sure you're aware of. You do the length times the width times the height, and you end up with volume. If you're doing these in units of centimeters, which we usually are, all of those centimeters will be multiplied and they'll be centimeters cubed, which is actually the same thing as a milliliter, which is really interesting. So we get milliliters, which is a unit of volume. What if we have an object that has an irregular shape? Okay, I feel like it just got dark in here. Like a rock or a marble or something that doesn't have sides. We can do that through something called water displacement. You'll want to write that down. Water, which I'm sure you can spell, and then displacement, looks like this, displacement, water displacement. And that is a way of moving water to tell how much volume an object has. So you start by filling up a graduated cylinder with a random amount of water. Doesn't matter how much is in there before, as long as it can cover your object. So let's say we have 10 milliliters of water in here before. Then I drop in my irregularly shaped object, and now I'm at 13 milliliters. Well, how would I know the volume of my rock or the object I added in? Well, all I have to do is subtract the two, right? I had 10 milliliters before, now I have 13. So guess what? These 3 milliliters in between 10 and 13, that was due to the rock. So these are the steps. You want to write them down on your notes. We're going to be doing that in the lab. All right, to measure mass, we always, or to measure weight, I'm sorry, we always use mass, and we use the units kilograms and grams. Most of the time, we use one of these bad boys. It's an electronic balance. Be sure you actually take the lid off when you measure anything on it, and then be sure that you press the 0 button so that before you put anything on it, it's zeroed. If we look at the volume of this container, I see the big lines, they represent the tens, right? And then these small lines, let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So since there's 10 small lines, that means that I'm measuring to the ones place, right? In between the 70 and the 80. Each of these marks are 1. So 71, 72. I can see that I'm kind of right at the 75 line right here. If anything, I might be slightly below the 75 line. So let's just say I'm at 74, okay, because I'm right below the 75 line. And what's interesting about science is that you, as a scientist, you are like God in the lab, okay? You get to determine an estimated digit. You get to determine the next digit place. So the next digit place for us, since we're measuring to the ones, right, that's the increment lines on our graduated cylinder. They're to the ones. We can estimate to the tenths. We get to estimate this next digit. So I'm going to estimate 74.9 because I'm almost at the 75 line. Now you could have estimated something different. You could have said it was right at 75, right? Well, 5 would have been your measured line. That's your last measured line. But you still have to estimate to this next digit, right? You have to estimate to this digit right here. So you could estimate 75.0. So let's look at another example. When I talk about significant figures, I'm talking about measured or estimated digits. Estimated, meaning the digit that we guess as a scientist, and measured is the one that's on the line. So if I look here, I can see that this ruler is obviously to the ones place, so the ones place is measured, right? And then, so this is the ones is measured, the ones are measured. But then I see I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 marked lines in between them. So it's also measuring to the tenths place. So since these are all measured digits, okay, they're measured, they're significant. We call them significant figures because they're measured. All right, but we know we always have to estimate the digit after the measured one. So we have to measure, we have to estimate the hundredths place. That's what comes after the tenths. So we have to estimate this digit right here whenever we're measuring the nail. We can't just stop at the tenths. We have to estimate the next digit. So all 3 of these digits, the measured and the estimated, they're considered significant. So significant figures are measured numbers and estimated numbers. And I'm abbreviating because it's hard to write on the screen, but on your notes you don't want to abbreviate them. You want to write down what those stand for. Measured digits are measured numbers, and estimated numbers are significant. So for this nail, it looks like it's 1, 2, 3. It looks like it's in between 6.3 and 6.4. So I might put 6.35 as my number. Remember, 5 is what I estimated. 6 and 3 were measured. So you report what's known with certainty. This would be what's known with certainty. And you add 1 digit of uncertainty, which is your estimation. Okay, but all 3 of them are significant numbers. Okay, so when I show you a value like this, I show you a number like this, and I say, how many significant figures are in this number? You should tell me. If we look at this first value right here, we can see that this last digit was estimated, right? Because remember, we always estimate the last digit, right? So the only reason they would put a 0 there is if they had to estimate that, right? We know the device they used was measuring to the tenths place, and they had to estimate to the hundredths, right? Otherwise, the 0 wouldn't be there. So these must all be measured marks on their device, and then the 0 was what they estimated. So all of these are significant, so we have 4 SigFigs. That's how I abbreviate significant figures. Now let's look at this next number. This next value, the last number is obviously the estimated one, right? 2. They estimated 2, which means every number before that must have been measured. So here we have 3 significant figures. Okay, this next number is a little bit tricky. In this first value, I knew this 0 was estimated because there was a decimal right here. And so what that decimal means is that this 0 right here, it's not holding a place. They put it there on purpose, right? They could have put 23.5 and it's the same number. But since they put the 0 there on purpose, it must be estimated. But what about this 0? This 0, it has to be there in order to be 5,280, right? So I don't know if the 0 is estimated or if the 0 is a placeholder. So the way that we know it's different in science, and you won't see this in any other class except chemistry, is if the person who measured this, if they want that 0, if they want to tell you that that 0 was estimated, they estimated that 0, they're going to put a decimal point right there. If there's a decimal point, then that 0 was estimated. And they're trying to tell you that by putting a decimal. But if there's not a decimal point there at all, then we're going to just assume the 0 is holding a place and it's not significant. It wasn't estimated and it wasn't measured. So this we're saying is not significant. The 8 must be the estimated, and then the other 2 must be measured. So this has 3 SigFigs. Now let's look at our last number. Our last number, these zeros are obviously holding a place. So they're not significant. They weren't measured and they weren't estimated because they're in front of the number. They're obviously holding the place for 0.080. But remember, since there's a decimal here, this 0 must be significant because they could have written 0.08, right? So why would they put the 0 at the end? Why would they purposely put a 0 at the end? Well, that 0 is not holding a place. They put it there on purpose because it was estimated. So this 0 is estimated, and then this 8 was measured, so there's only 2 significant figures. So what I've done is I've walked you through 4 different scenarios. I now want to show you these rules that we come up with for significant figures. I've already applied all the rules for you right now, but I want to show you kind of what they look like. So our first rule is that all non-zero numbers are significant, right? All regular numbers are either measured or estimated. Okay, so they're always going to be considered significant. The issue is when we have zeros. Zeros get a little tricky. So these are the rules for zeros, and all this should be written on your notes. Oh, it says font. It's supposed to say front zeros. Any 0 in the front of a number, at the very, very beginning of a number, like the one when we looked at here. These are the zeros in front. They are never significant. They're never, never, never measured, and they're never estimated. They're just placeholders. So when I say it's not significant, I mean that they're not measured numbers. They're just placeholders. Middle zeros are always significant. So like, I think this was the number, 402. I think that was the example I used on the other page. This 0 is significant. It was measured, okay, because we have this value here. So the 2, the only reason the 2 is there is because it was estimated, which makes the other numbers measured, right? So any 0 inside or in between 2 actual numbers, it's always significant. The ending zeros are what get tricky because the front ones never count, the middle ones always count, the ending ones sometimes count and sometimes don't. So remember when I looked at the 5,280, there wasn't a decimal point present, so this 0 we consider a placeholder and it's not significant. However, if I use this exact same example, 0.080, see how there was a decimal present right there? Since that decimal was present, this ending 0 is significant because it's not holding a place if it's coming right then. We only put it there because it was estimated. So if the decimal point is present, it's significant. If the decimal point is not present, those zeros at the very, very end are just holding a place.